All right, good afternoon, everybody. We're going to go ahead and get started. This is the research results presentation for the student study role of sulfates on highway heaving in Lake County, Ohio. It was performed under the direction of Dr. John Farver at Bowling Green State University. He had two students who were working on this project, Angel Mandel and Monica Weir. Monica is here to give our presentation for us today. For those of you who are participating via the web, please make sure you mute your telephone right now, or you'll be sharing all of your deep, dark secrets with everybody. If you do not have a mute button, you can do so by pressing *6 on your phone. I will let you know that this presentation is being recorded, and a recording of it will be available on the ODOT research website, along with the final report and the PowerPoint presentation for download later, or you can share it with some of your colleagues who might not have been able to join in. Webinar participants, if you have a question during the presentation, on the lower left-hand corner of your screen is a chat pod. Please feel free to type your questions there. We are going to hold all questions until the end of the presentation. At that time, Monica and Dr. Farver or Angel, who are participating online, will be answering your questions. With that, all yours, Monica.
Okay. Yeah, my name is Monica Weir. I'm an undergraduate at Bowling Green State University. I actually graduated in August, so not an undergraduate anymore. Yeah, for the last year and a half, we've been working on this project, the role of sulfates on highway heaving in Lake County, Ohio. This is the outline of the presentation. We're going to do a statement of the problem, an introduction, and we have three objectives. Objective 1 is characterizing the boring samples that we looked at. Objective 2, synthesizing ettringite. And Objective 3, we performed some SWELL tests to replicate conditions in Lake County, Ohio. And then we have some conclusions and recommendations. The problem. In the summer of 2009, the existing pavement on Route 2 in Lake County, Ohio had to be removed and replaced due to heaving. And then in the late winter of 2010, there was longitudinal cracking discovered. Fall in 2010, the pavement was heaving up to greater than 4 inches. And then in December of 2010, some boring samples at 2 stations showed sulfate levels greater than 10,000 parts per million. And like we said before, the site location is Lake County, Ohio. I believe there was a picture there that did not come up. The geologic setting. Lake County is part of the Galian glaciated low plain till plain. The soil is the Conneaut Painesville. It's a poorly drained soil, silty glacial till or loamy material over silty glacial till on lake plain during the Wisconsin glaciation. And the underlying bedrock is the Ohio shale. This is late Devonian in age. It's a brownish black or a black shale deposited in stagnant and tropical seas. And the suspected source of heave in this area is ettringite. Sorry, our animations aren't working. It could be a problem later on. Should I keep going? Okay. Okay. So one of the things we looked at from the Texas Transportation Institute, they have outlined risk levels associated with stabilization of soils. The low risk is below 3,000 parts per million, moderate 3,000 to 5,000, moderate to high 5,000 to 8,000, and high to unacceptable greater than 8,000, unacceptable greater than 10,000. So what we like to focus in on is the moderate. We're looking for sulfates greater than 3,000 parts per million. Again, a restatement of our objectives. Objective 1, to characterize soils from borings along Route 2 in Lake County. 2, we're going to synthesize and learn how to identify ettringite so that we have a very clean lab specimen to compare to what we find in the soil. And 3, we want to create SWELL samples to replicate conditions on Lake County. Okay, so objective 1, we looked at some boring samples. We had 28 samples that we received from Jeff with ODOT. Most of the samples, 22, were from the subgrade soil, with the remaining samples from different depths like top, middle, bottom. We did sulfate analysis on these using the Texas 145E colorimetric method. And we chose this method because it seems to, within the literature, it seems to be the more reliable method to use. And also, ODOT had trouble with some of their first sulfate results, and they were going to redo the results using this method, so we decided to use this method too so that we could cross-check each other. And then we also looked at the mineralogical composition using XRD analysis of the same boring samples. Again, we chose the Texas 145E colorimetric method. This was recommended by Little and Nair, and it's preferable over the ASHA TOT290 test. That test has been known to report much lower sulfate values. Our sulfing test procedures, we passed the soil through a number 40 sieve. Then we took 10 grams of that soil and mixed it with 200 milliliters of deionized water. We shook it really vigorously for 1 minute and allowed it to set for 24 hours. It was then filtered with a millipore filtering system, which you can see over to the right there. And we used a 0.45 micron filter paper. Once we got the filtrate, we took, to get a 1 to 20 dilution, we took 10 milliliters of the solution, added 2 drops of hydrochloric acid, mixed it up, and then added a barium chloride packet to it. And then we would put it into our colorimetry meter here off to the right. This unit only measures sulfate in the 5 to 100 milligram range, so a lot of times dilutions were needed. So we started like with the 1 to 20 dilution. Sometimes we dilute it 1 to 40 or 1 to 80 to get a sulfate reading. The first time we started sulfate testing, we took the reading and, right away as soon as the sample was prepared, and we did it 2 more times after that. So we had 3 readings within a minute. We averaged those readings, and that was what we used for our sulfate results. However, as we were going through the process, we also took note of what the sulfate reading was at 5 minutes and what it was at 10 minutes. And we ultimately determined that 5 minutes when using the barium chloride packet is the ultimate wait time. As you can see down here, the difference between the initial reading and the 5-minute reading results in a 90 parts per million difference, the average results. And the difference between waiting 5 minutes versus 10 minutes is a difference of 52 parts per million. So just due to time and everything, especially if you're testing a lot of samples and you want a good sulfate reading, 5 minutes is the ultimate, is a good wait time, the optimum wait time to use. So we looked at 28 boring samples, but we only had 23 samples where we actually had results that compared to ODOT. So we did a comparison of those 23 samples, and 5 of the 23 came back ending up in different risk categories, and that's what we're ultimately concerned with. It's really hard, even within the own lab, to get the same sulfate parts per million result every time you do the test. So what you're really hoping for is to get into the right risk category. And so as you can see, we were pretty successful. Only 5 of the 23 times were we different. 3 of these times were significant, which resulted in a change from a low risk to a high risk category. And let me get the drawing function over here. The ones in red are these. There we go. The ones in red are the significant. Doesn't look like I can get my pointer to work here. There we go. Well, you see over here, it was below, ODOT's result was below 2,000, or it was below 3,000 parts per million, where our result was above 3,000 parts per million. So those are significant differences. 2 of the 5 were not significant because both of our results were above 3,000 parts per million. And in the graph at the bottom, it's just kind of a comparison visually of our results. And you can see that we did a really good job, the 2 different labs, of following each other. And also that a lot of the results were above 3,000 parts per million in sulfate. We also, with these boring samples, we took the same soil that was used to run the sulfate test. We used that exact, we ran actually an XRD on it first before we used that soil for the sulfate testing. So the XRD results corresponded with the sulfate of the same boring. And to go over the XRD procedures a little bit, you first have to grind down the sample and crush the soil. And you can do it 2 ways. We have this aluminum holder where you can put the crushed soil in that, or just use a small amount of soil and put it on a glass plate. And our system that we have is the RIGAQ MiniFlex 2 X-ray diffractometer. And down here at the bottom is just an example of what a scan looks like. Most scans are run from 3 to 70 degrees at 2 theta at a 1.5 degree per minute scan rate. And then slower scans, especially if like we're looking for ettringite, they'll run slower from 3 to 40 degrees 2 theta at a 1 minute look. And the ettringite peaks are characteristic at 9.14 degrees and 15.86 degrees. And that's what the little yellow arrows down at the bottom are pointing out, the 9 and the 15 degrees for ettringite. Okay. With the boring samples that we looked at, all the samples were predominantly quartz with muscovite. It's kind of hard to see with that scan there, but the largest peak there is quartz, and then the smaller peaks down at the bottom with the green or with the red lettering, that's the muscovite. There's also some clinicore in there. And then the other common minerals were clays. There was a lot of clays in there, clinicore, kaolinite, and illite. 57% of the boring samples contained measurable gypsum, anhydrite, or a combination of both. Okay, so a summary of our objective 1. We determined that the Texas method was the preferable method to use when sulfate testing, and that between the 2 labs, BGSU and ODOT, our sulfate results for the boring samples were pretty consistent. We found a lot of sulfates in the boring samples above the 3,000 parts per million risk, and we also found gypsum and hydrite in over half of the samples. But as you'll see as we go on through this talk, gypsum is very heterogeneous in the soil. You can find it a lot in some samples and not at all in others. It's not evenly distributed through the soils. And then, yeah, and I guess I kind of covered that with the bottom thing. So the difference in sulfates a lot of times are due to the heterogeneity of the gypsum distribution and not the testing method. The testing method is actually pretty reliable. So. Objective 2, synthesis and characterization of ettringite. And what we wanted to do with the ettringite synthesis was to create a pure form of ettringite crystals so we could see what it looked like in the SEM and what it looked like in the XRD and have something to compare to when we looked at our soil samples. So it was important to get a pure sample so that we could get a good XRD spectrum and EDAX analysis with at the SEM. And to create the lab ettringite, we looked at a journal article by Cody et al. In 2004, and we adapted it a little bit. And that was mainly just in the lab equipment that was available to us. So what we did was we saturated calcium oxide solution, and it was prepared with the dry nitrogen gas and was bubbled through the solution overnight to purge any carbon dioxide. What happened was we ran this the first time and didn't purge the carbon dioxide, and what you end up with is calcite. Then we saturated aluminum sulfate solution. The saturated aluminum sulfate solution was then added to the carbon oxide solution and bubbled with the dry nitrogen gas for another 8 to 12 hours. After 1 hour, fuzzy precipitate starts forming on the glassware, and within 24 hours the reaction's complete. And then we filtered the precipitate and then place it in a desiccator to dry overnight. And as I said before, if you do not run the nitrogen bubbler on the solution throughout the whole process, the carbon dioxide ends up resulting in calcite instead of ettringite. And now we're going to get back to the lab ettringite in a minute, but we're going to, I'll explain to you a little bit about the SEM EDAX process here. SEM is a scanning electron microscope, and the one that I used is a Hitachi S2700. And what it does is it focuses a beam of electrons on a specimen, and as there's many emissions off of this, the electrons hitting the specimen, and one of these is secondary electrons, and now those are what actually produce the 3D images that we'll be seeing today. And then along with the SEM, we have software, EDAX software, energy dispersive spectroscopy, and this software looks at X-rays coming off, X-ray emanations coming off of the specimen when the electron beam hits it. When the electron beam hits the specimen, electrons in the outer shell are dislodged, and they're replaced by electrons in the outer shell. The difference between the inner shell and the outer shell electrons is a characteristic X-ray that is characteristic of a specific element, and that's how we know what elements are present in the sample. The SEM sample preparation is kind of involved. With the lab ettringite, it was just a matter of allowing the sample to air dry in the desiccator for 3 days, and then affixing some of that white powder onto a stub. But I'll go ahead and explain some of the soil preparation right now. With the soil samples, those are air dried for at least 3 days. We don't put them in an oven because we want to preserve any mineral structures, especially with ettringite or thomsite. We don't want those structures to break down. And with the larger soil samples, rather than grinding it like you would in the XRD or cutting it, I'd simply break off pieces of a larger piece and put it on the stub. The aluminum stubs are 12.7 millimeters, and because they're made of aluminum and ettringite is made up of aluminum, we place either a carbon adhesive or a carbon planchet over the top of the stub so that the EDAX results we're getting represent true aluminum readings. And the stub and the sample are fixed. The carbon planchet and the sample are fixed to the stub using liquid graphite, which shows up as carbon on an EDAX reading. And once the sample is affixed to the stub, it again has to be allowed to air dry for 3 days. Once it's dry, you can either coat it with carbon or AUPD, and this makes the sample conductive to attract the electrons to the specimen. And the run conditions that were used for the SEM was always an accelerated voltage of 20, kV of 20, and a working distance of 12 millimeters. 12 millimeters has to be used with this machine because it's the optimum angle or the optimum distance for the EDAX. A lot of clays appear as thin hexagonal plates. And gypsum, this is actually a very small piece of gypsum, but everything it appears much larger in the SEM. So as you can see, gypsum is tabular with perfect basal cleavage, so it's very flat, plain cleavage. And ettringite needles, this is a close-up on it. A lot of times ettringite needles might look flat, but they're actually six-sided and they have a hexagonal shape to them. And soil, and then likewise soil mixed with cement will appear very platy. So as we're going through some of the pictures, you might be able to pick out some of these things. So now we're back to our lab ettringite, and we looked at the sample with the SEM, and this is what it looked like. And so we did see the six-sided needle-like hexagonal morphology. And here in the lower left, you can see this is a EDAX spectrum, and you can see there's the spectrum for the oxygen, aluminum, sulfur, and the high amount of calcium in there. Over here, these are, I did several samples, so this is like an average of all my samples of the elemental weight percents. So again, with ettringite, you're always going to have very high oxygen and calcium. With sulfur and aluminum, the carbon is from the carbon planchet and from carbon coating the specimen. And what we did was, this is the results we got from the SEM. We took the empirical formula of ettringite and calculated the atomic weight percents for each element. So if you compare those, what you should be seeing is oxygen is about 50%, and we're, very close to that. Calcium, very close in the 30s. Sulfur, around 12. This one was close to 11. And aluminum, 6.977%, 7.21%. So our results were actually very good. We were very close to the actual atomic weights going from the formula. And looking at the lab ettringite with XRD, this is a spectrum of the initial run without dissolving the CO2 with the nitrogen gas, and what you see is the big calcite peak in the middle there. So all we got from that run was calcite. And then when we bubbled the solution with the nitrogen gas, we get the characteristic ettringite peaks. Right here, we actually, with the lab ettringite we created, we were able to look at this with a petrographic microscope, so that's what you're seeing there. You could actually, the needles were pretty large. So we were able to create the lab ettringite. We were able to see it with a microscope and also with SEM images. We were able to get a EDAX composition to compare to, and also to get a standard with the XRD. Okay, and now on to objective 3. Sorry. I took a drink of water. So, with objective 3, what we wanted to look at is we wanted to perform SWELL tests with the non-stabilized soil to replicate conditions that we were seeing along Lake County Route 2. And as I've said before, we obtained 6 buckets of soil from ODOT. The stationings are 729, 730, and 730 plus 80. Each station had 2 buckets. One consisted of cement-stabilized soil and the other one of non-stabilized soil. And these areas were chosen because they were areas with significant heave and where full-depth pavement repair had to be done. First, we wanted to characterize the non-stabilized soil. And what we found is the non-stabilized soil is primarily brown and gray sandy silt. And you could visibly see a lot of clay in the soil. It might be hard to see on this image, but there is a gray clay layer running through the middle of that sample, and that was very common in the non-stabilized soil. There was also a lot of gypsum crystals. They were finely disseminated and also very visible to the eye, up to 2 centimeters in size. And we also saw a lot of black shell as well, as small as like a couple millimeters up to a couple centimeters in size. So what we did first was look at the non-stabilized soil with SEM and EDAX. And these results are based on 21 samples, 7 samples per station. And this right here is a typical SEM image with a typical EDAX spectrum. So what we're looking at is a sample of station 729 here. And non-stabilized soil, as you can see, it's just this very platey, flat image that you get of the soil. And then here is average elemental abundance for the 21 samples. So you're getting a lot of high oxygen, silica content, a lot of calcium and iron and aluminum with some minor amounts of potassium and magnesium, titanium, and sodium. The sulfur in the spectrum is actually misleading. You don't normally in non-stabilized soil pick up on that high amount of sulfur. That's actually due to a couple samples where I focused in just on gypsum alone. So that's why we're getting the high sulfur in the averages there. But as you can see from the EDAX spectrum on the right, there isn't a sulfur peak typically when you're just looking at non-stabilized soil, unless you happen to hit an area with a lot of gypsum. And this is kind of a picture of just soil, how we would put it out to air dry. If it was an SEM sample, I might take one of those little pieces that looked interesting or break off a small piece from a larger area. If it was XRD, then the sample would get ground down to very fine powder. And with the XRD, looking at non-stabilized soil samples, the samples were primarily quartz with muscovite, and you can see that big quartz peak, the largest peak at the top there, with the smaller peaks being the muscovite. And What we found is there is gypsum in the non-stabilized soil, but kind of like what we found with sulfate testing, the gypsum is very heterogeneous. See, it doesn't show up in every sample that's run. So we have, oops, up at the top here are 3 729 samples, 3 730, and 3 730 plus 80. You can see primarily in all of these, quartz and muscovite are the what's primarily making up the non-stabilized soil. There is some gypsum here that was found in 729, and then I believe, yes, some anhydrite down here in 730 plus 80, and then we have a lot of clays like Klinocore. Some of that was found in 729, 730. So again, non-stabilized soil, primarily quartz and muscovite. Then we looked at the cement stabilized soil, and it looks very similar to the non-stabilized soil. Not as much black shale class in the cement stabilized soil. And what we did notice that was different between these two soils is there's a lot of white precipitate in the stabilized soil. And so we really focused on these areas because they stood out. And also in reading literature, we thought that these might be, the white precipitate could be gypsum or maybe even ettringite. So we really started out focusing on those areas. And this is just a typical spectrum of ettringite here. And so now that we know what ettringite looks like, we wanted to see if we could find it in the stabilized soil. So in the XRD scan below, we're looking at a sample of 729 white powder. Looking at the white powder, we did find some ettringite, but we also found calcite. And when looking at a lot of samples across the board through all the stationings, what you find is that the white precipitate is mostly calcite. Here's another sample that was done on XRD looking at 730, and a lot of thaumasite was found. That is the green peaks down there. And then another sample, 730 plus 80, there was some ettringite along with some muscovite there. So what we did find, at least with the cement stabilized soil, using the XRD, if you do focus on the white precipitate areas, even though it's primarily calcite, it's often a good area to find also ettringite and thaumasite. If you focus on more of the areas that without the white precipitate, you'll get a lot of quartz. So here's some of the major components, again, 729, 730, 730 plus 80. And again, you can see a lot of quartz and muscovite, a lot of clays, some ettringite found here in 730, ettringite over here in 730 plus 80, and there's some thaumasite down here, a lot of thaumasite up here in 730. And then likewise, we did the same thing with the SEM. We looked at white areas and did find needles. So these are, we confirmed with EDAX spectrum that these are ettringite needles. So this is 730. And you can see in this picture the underlying soil in there and, you know, some cracks and fracture networks in there too. This is a close-up of the 730. This is 2 microns, the scale bar down there. I know it's hard to read. And this is 730 plus 80. Ettringite often appears different in the SEM images. This one, you know, there's a lot of radiating bundles here, and this is ettringite like growing strong. It's getting loose and starting to do these bundles and everything. You can see the underlying soil. here, it hasn't been confirmed, but I'm suspicious this might be more what primary ettringite looks like, because you can see it's more mixed in with the soil, it's more a part of the soil. It's not really loose and radiating. So it will appear in different ways. And then here's an example of it being more loose and radiating. And a close-up image of the needles. And that was 730 and 730 plus 80. With the cement stabilized soil that I had and just the samples that I looked at, for some reason 729 did not have as many needles as the other samples. It was primarily soil, but we did find evidence of ettringite needles in there. But a lot of the samples look like this on the left, where you're seeing mostly soil, but you will get areas of where you can see ettringite needle growth starting. And comparing the two spectrums, you can see that the main difference when going from a lot of soil with some ettringite to zooming in on the ettringite is that the silica content goes down, calcium goes up, and you'll get a sulfur peak where before there wasn't one. And then, of course, aluminum is important with ettringite, but you can also see that a lot of times in the soil. So this is the spectrum up above is from one sample. That's what a typical spectrum looks like for cement stabilized soil. And then down below, what we have is the average elemental abundance for 30 samples. So again, high oxygen and aluminum, and this is a true sulfur reading. And then all your other elements that would be consistent with the minerals in the soil. And comparing this to the pure lab ettringite, you can see that the amounts, they come in pretty close to what, pretty close to the pure. They're just being diluted by the soil and the other minerals that are in there. Okay. So what we wanted to do, again, we're working towards doing our SWELL testing, is we wanted to take the non-stabilized soil and the stabilized soil that we were given and sulfate test it to see just how much sulfate was in these soils. And we used the Texas method. We looked at 3 samples per station, so a total of 18 samples, and we used the 5 minimum optimum wait time. So here's the results. On the left is the non-stabilized soil, and on the right is the stabilized soil. If you look from non-stabilized soil, the pHs are around 7.9 or 8. And if you look at the individual sulfate levels, they're all over 3,000 parts per million. And the average is well over 3,000 parts per million for non-stabilized soil. With the stabilized soil, the same thing, all over 3,000 parts per million. So what this is telling us, the soil in Lake County on Route 2 is very high in sulfates. So there is definitely a risk of ettringite growth in these soils. And if you look at the pH of the stabilized soil, just by adding the cement, you're getting pHs around 9 and 10. But again, you need a pH of 10.5 for aluminum to start to break down in the clays in the soil, providing that additional aluminum to grow ettringite. So there's other factors that need to happen all together at the same time to create the ettringite. So after doing the sulfate testing, given that the threshold level for sulfate or for SWELL damage is 2,000 to 3,000 parts per million, and given the high sulfate readings for the non-stabilized soil above 3,000 parts per million, and that the pHs were getting pretty high there on the cement stabilized soil, we determined for our sulfate, or for our creating our SWELL samples, that additional sulfate in the form of gypsum wasn't needed, that we felt pretty confident that swelling could happen and ettringite growth could happen without the addition of any sulfates. In modeling the swell samples, we looked at a Texas study by Harris et al. 2004, and we followed that study pretty closely. We only made a couple of changes, and we made these changes to better represent Ohio conditions along Lake Route 2. The one thing was, after sulfate testing, we determined that we didn't want to add additional gypsum because that wouldn't really be representing the conditions at Lake County. Whereas the Texas study, they added additional gypsum, fine-grained and coarse-grained, because their soils are sulfate deficient. Their soils are very dry there, and then they'll get a heavy saturation of water from a thunderstorm. So they took all their samples and air dried them for 3 days. So what we did to be consistent with that study was took half of our samples and air dried them for 3 days, but the other half we kept moist because we felt that that more represented Ohio conditions in Lake County. To make the samples, we made them here at the ODOT facility. The soil, we used non-stabilized soil, and it was passed through number 4 sieve first. We then added 6% St. Mary's cement to that, and we wanted it to be the wet side of optimum, so we were trying to hit a target of 16% moisture with the addition of distilled water, and the actual samples came out somewhere in the range of 15 to 22%. Some of them were 16, some of them were a little short, some of them over. And again, we used the ODOT facilities, the standard Proctor machine. The rammer was 2.5 kilograms and 305 with a 305 millimeter drop. The molds we made were 4 by 4.5 inches, and each sample involved 3 soil layers with 25 drops per layer. And we made a total of 12 samples, 4 samples per station, and to the right you can see the breakout of how these samples were designated. So we had 6 wet, 6 dry. Of the 6 wet, 3 were placed in distilled water, and 3 were placed in a 7,000 parts per million sodium sulfate solution, and likewise the same was done with the dry samples. We created samples here at ODOT, put them in plastic bags, and drove them back to BG, so they were left overnight to cure in the plastic bags. Then the next morning, the dry samples were taken out and measured, and then just left out and lightly covered to air dry for 3 days. After they were air dried for 3 days, we measured them again, put them in latex membranes, and then measured again, because the latex membrane does actually add some, create some difference in the measurement. The wet samples, after being cured overnight, were immediately placed in latex membranes the next morning and initial measurements taken. This is what the samples look like. We had 2 chests, so one had distilled water in it, and one of them had the sodium sulfate solution in it. So there were 6 samples in each chest. And there was a porous stone on top of the sample as well as on the bottom of the sample. So the sample was never in direct contact with the water or sodium sulfate. That solution would wick up through the porous stone into the sample. And there were 6 measurements taken per sample, 3 height, 120 degrees apart. You can see the markings on the top of the porous stone there that we used. And then 3 for circumference, 1 at the top, middle, and bottom. And then these 3 measurements for each one were averaged and used to calculate the volume change of the sample. And the measurements were taken every day for each sample for 56 days. And here's the results. So we found it made better sense, or it was easier to look at by separating out the wet samples from the dry samples. And as you can see here, 730 swelled the most, both in the wet and the dry samples, followed by soil from station 729, and then soil from 730 plus 80. And the dry soils swelled slightly better than the wet samples, but not, statistically significant difference. As well as you can see, the thin lines on the top are the sodium sulfate samples, and the thick line is the sample from the same stationing, only in water. So you can see that the samples in the sodium sulfate performed slightly better than the water samples. But again, they tended to stay pretty close together. And one thing that you'll notice is that the station 730 plus 80 that had the highest sulfate amount, over 6,000 parts per million average sulfate, swelled the least. It only swelled 0.5 to 1.5%. However, 730 and 729 swelled quite a bit, and both of those were over 3,000 parts per million, with 730 obviously being the one that swelled the most. Here's just another way of looking at the samples. This is looking at the average circumference measurements on the bottom versus the average height. And what you can see is 730, the samples that swelled the most, they pretty much continued swelling throughout the whole 56 days. Whereas 729, you can see it kind of stopped growing midway through the experiment and over here. And then 730 plus 80, which there was a small percentage of swell. It swelled a little bit in the beginning of the experiment and then pretty much stopped. And these, the squiggles back and forth are just a result of the slight differences in the measurements from day to day once the swelling had stopped. Some observations that were noted during the swell test. By day 4, solution had begun to be visible rising up the sides of the sample. I don't know if you can see it here, but that's about the moisture line there. So this is a water sample. So the water has risen up through the sample and is about right there by day 4. And here is the sodium sulfate sample at day 4. And there's the line right about there. Initially, when looking at the circumference measurements, when measuring the bottom here versus the middle and the top, initially the bottom measurements were the largest measurement, which makes sense given how the moisture was rising through the sample, followed by the middle and the top, but over time that proved not to be consistent. And this could be due to a number of reasons, primarily because there started to be cracking as the swelling continued. And like I said before, in general, the dry sample swelled slightly more than the wet samples, and the sulfate slightly more than the distilled water samples, but again, not too significant, not a lot of significant difference between those. And a physical description of the swell samples. After 56 days of measurement, the latex membranes were removed and the samples were allowed to air dry. So here you can see a lot of visible cracks in the samples. We cut the samples in half with a diamond saw and then allowed them to air dry out. And another thing we noted was that with the sodium sulfate samples 3, 8, and 11, they had a white precipitate ring around, this is the bottom of the sample, around the bottom of the sample. This particular sample has two, one that's a little bit larger than the other one. The small one's like a millimeter, and the other one maybe half a centimeter. And we noticed these rings on several of the samples. On the water samples, we noticed them on 6 and 9. And another thing to point out was that the only samples that had these rings were dry samples. None of the wet samples had these. And here's another picture one on sample 6. Most of them look like this. Sample 3 is kind of unique. It's hard to see here, but it's a very thin white ring on the outer edge of the sample. And so we wanted to focus in on some of this white precipitate that we were seeing on the SWELL samples. And like, before with the stabilized soil, where we really focused in on that white precipitate, we did the same thing with the SWELL samples, hoping to find ettringite or gypsum. And what we found was the white precipitate is primarily calcite. And so this is an XRD scan down here showing a sample from 730 and showing the calcite peaks. And what we found, at least with the SWELL samples, it was easier to find ettringite, not in taking a heavy amount of the white precipitate, but like sampling near it, or actually even going to the middle of the SWELL sample and just getting parts of the soil that looked just very brown with no white precipitate. We were more successful in finding ettringite in those areas. And with the SEM, looking at the SWELL samples, it didn't matter where we sampled from. With the SEM, we could find the ettringite needles in the white precipitate area or from the bottom, middle, or top sections. And we also found ettringite needles even in the samples 1 through 4 from station 730 plus 80 that had a very little amount of SWELL. And so here's some SEM pictures. So this is 730 plus 80. Again, a very, not a lot of SWELL on this, but when you look at the samples in SEM, you do see the characteristic ettringite needles. And then another 730 plus 80. This one was in water, and it was a wet sample. Here's the 730 sample. This was a sample that swelled quite a bit. You can see the ettringite needles are much more abundant in this sample, and they're more flowering and radiating. And this was a dry sample in water. And a sample from 729. Got some radiating ettringite needles here. And another from 729. And this is just kind of a zoom out picture showing where you can see the soil and then mixed with, different bundles and areas of ettringite needles. And so down below is an average elemental abundance of all of the samples for the SWELL samples that were looked at with EDAX. So again, the characteristic high oxygen, calcium, the silica coming from the soil. We got our aluminum here in the 6 to 7% range, and the sulfur along with the other characteristic elements for the soil. So a summary of Objective 3. We wanted to replicate soil swelling using the material from Lake County Route 2. And what we found is some of the high sulfate concentrations didn't necessarily indicate the largest SWELL performers in our SWELL samples. And we feel like this is largely due to the heterogeneous distribution of sulfates in the soil, primarily gypsum in the case of Lake County. However, the soils that did swell a lot in our SWELL test were well above the 3,000 parts per million. So we still feel like 3,000 parts per million is a good limit to set on your sulfate values. And we did establish that ettringite is linked to soil swelling it was present. This should be in the stabilized, not non-stabilized. It was present in both the stabilized soil and in the swell test lab specimens that we made. So in conclusion, the Texas 145E colorimetry method, we feel provides a very rapid and reliable sulfate testing analysis to use. We learned that dissolved carbon dioxide in calcium oxide and an aluminum sulfate solution promotes the growth of calcite over ettringite. And then in laboratory experiments using soils from Lake County, we showed significant swelling and the formation of ettringite. However, the swelling doesn't always relate back to the amount of sulfate that was present. And some implications and recommendations. Following Little and Nair 2009, you should look at your sulfate contents and determine the heterogeneity of the sulfate distribution in your soil. And then sulfate risk levels should be considered when using any kind of calcium-based stabilization. And then following Harris et al. 2004, this is primarily with the SWELL testing is what it's referring to. It would be interesting to do further SWELL testing and play with the mellowing times and the amount of water that's added to the samples, and really look at primary versus secondary ettringite formation, because what we suspect from our low SWELL performer here, 730 plus 80, even though it had the highest amount of sulfate, if you look back at the XRD scans, it has the highest amount of gypsum over the other two stationings. So what we feel is the gypsum in it was very finely disseminated. We looked back at the water content that was put in the soils when making the SWELL samples. 730 plus 80 had the highest amount of water put into it. So what we feel might have happened with this sample is that there was more primary ettringite formation, which then slowed down secondary ettringite formation. But additional testing would be needed to confirm that that's what happened. Therefore, considering things like mellow time and the amount of water and the amount of sulfate put into the soil initially is important. As for acknowledgments, we'd like to thank Jeff Wigdahl at ODOT for all of his help. He was a tremendous help. And Marilyn Kayer at BGSU for her help with SEM and EDAX, and then the ODOT Student Studies Program for funding this research project. And that's it. Are there any questions?
So we're going to open up for questions right now. For those of you in the room, if you have a question, just raise your hand and we'll call on you. Those of you on the webinar, if you have a question, you may type the question in the chat box, or you can unmute your phone by pressing *6. Monica, if you have questions in the room, you'll need to repeat the questions so the webinar participants can.
Okay. Yes.
Okay.
No, sorry, Neil. Sorry, Neil. I was looking at the screen.
In the SWELL testing, your goal was to take a non-stabilized soil and reproduce what happened on Lake 2.
Right.
You were trying to stabilize it first and then compare it to the swelling that happened. Did you compare it back to the swelling that happened on Route 2 at those sites to see if you still get the same amount of swelling in the non-stabilized soil?
What we were trying to do was take non-stabilized soil from Route 2 and use the same amount of cement and water that was used out on Route 2. And I guess we didn't compare directly with the amount of heave that happened out there, but we wanted to see, can we make this soil swell?
Yeah.
Can we?
That we normally set as acceptable for just when we 1.5%. The highest sample when we took took the sample, mixed in, 6% cement is maybe a little high, but that's kind of what was used out there. We got, what, 9-10%? That the soil that was out there made it through all the checks saying it was okay, but obviously in some areas it was not. And under this location, using that same procedure, we were far and above. So that would be a no-go if it happened to.
On the Solmacite
Mhm.
that was formed, did you try to form that, or you just saw it in there? And did you do anything temperature-wise in your cure to try and create it? And
Hang up on myself.
what's a lot of
Okay.
Hang up on.
With the Sulfates that we found in the XRD results that you're seeing, that was in the stabilized soils that came directly from Lake County in the bucket. So that had been cement stabilized soil. So that cement stabilized soil out there did have thaumasite in it. When we did our SWELL testing, in order for thaumasite to form, you have to control the temperature. It has to be below 15 degrees Celsius. We didn't have that ability to do that in our lab. So for this run, we tried to focus on ETTRINGITE. If you wanted to see if thaumasite could form in these soils, you'd have to do the SWELL testing again and control the temperature and keep it below 15 degrees Celsius.
But you found it in
But
the
it
stabilized.
was in the stabilized soil, yes, from root 2. So my guess, I mean, you never know until you try, but my guess is that yes, it probably could be created.
But silicate versus the sulfate.
Yeah.
That's what she was finding in the field samples up there.
We do have a question from the webinar. Would results differ if you tried using a brine solution to hydrate samples?
Versus like the sodium sulfate? Are we talking about the
It could, and I'll just, the only
Okay.
the only difference is maybe the solubility of the gypsum in the soil. With sodium chloride, I think that may change the solubility of the gypsum that's in there, so you may release more of that in there. I can't really speak to the aluminum solubility or anything, but it could change the speed and the reaction and the solubility of the gypsum in the soil.
Okay, with regards to the SWELL test samples, were concentrations of aluminum recorded for the different samples to determine if aluminum could have been the limiting factor causing lack of SWELL in 730 plus 80?
With EDAX, we, for the samples I looked at, we did record aluminum. I guess we didn't specifically look at what was the limiting, if aluminum was the limiting factor specifically with that sample. So that could be, that could be a cause too.
I wanted to jump in here too. That was one sample that was ground a little bit finer. There was a little miscommunication between number 4 and number 40 sieve, and particle size may have been a mitigating factor in that one.
For those in the room, that's Angel, the other student that worked with Monica on this project. So if it sounds like she knew what was going on, it's because she grind all this sample and stuff like that in there.
Yeah, and what she's saying with 730 plus 80, a large portion of that sample, most of the first well testing, it was run through a number 4 sieve for that particular station. A lot of it got run through a number 40, so it was a lot finer than the soils from the other stations. So that could have played a factor too, that any gypsum or sulfates in there had a higher surface area, so they would react quicker. But again, it didn't swell as much, so in reacting quicker, that's why we thought maybe it had a higher primary ettringite formation and therefore secondary So it had run its course, and there was less secondary ettringite formation.
Kirk has a question.
Using colorimetric methods and the larger dilutions, what is the expected error of the results?
I did do error on that. Sorry, we didn't put that together for the presentation today, but we can send that to you if you wanted to send us an email, because we do have a spreadsheet with that information.
I guess I'll just chime in. There was a lot of talk about ettringite and then calcite. And then I think it was a pretty good discussion on if we're not bubbling or removing the carbon dioxide of a system when we try to grow ettringite in the lab, we get calcite. If we mitigate the carbon dioxide, then we can actually form ettringite. So some of the things that we look at, the question would be, some of the things that we look at that are calcite, they could form maybe ettringite, but they were exposed to carbon dioxide. So when you looked on the outside of the specimen, would it be realistic to assume that that doesn't represent the soil in the field? We don't have soil in the field in little cylinders.
Right.
When you looked on the inside of the soil, that's where you discovered the ettringite. On the outside, it was calcite.
Calcite formation, yeah. So obviously in the field, the soil is buried. It's not exposed as much.
Until it cracks, and then maybe pathways. Okay.
Does calcite maintain its volume? Are we okay with calcite?
Yeah, it doesn't have the water that wants to go to it. So, yeah. We better be good with calcite. Our road bases are built out of limestone, so that's calcite.
Okay, if there are no additional questions, we're going to go ahead and conclude this presentation. We would like to thank Monica and the rest of the research team, Angel and Dr. Farver, for their assistance with this project. The final report for this student study will be available on the research website. The link is written in the chat box. It'll be up there in about a month or so, as well as a recording of this presentation and the PowerPoint. If you have any additional questions you would like to get answered, you can feel free to email those to research@dot.state.oh.us. I guess I gave you guys the email address in the chat box, not the website. I'll put the website up in just a minute. But email all your questions there, and we will forward those on to the research team for them to answer. Otherwise, we would like to thank you all for participating. You are free to go.